In this lecture, we'll talk about drawing Lewis structures and specifically focusing on resonance structures of some organic species. Okay, first we will consider the HCO2 minus, or the formate ion. Right? And we've done this enough. I'm going to move forward, right? So if we look at the connected structure, we end up with something like this. If we distribute our electrons using the rules we've established before, we run out of electrons when we get here, right? And so that leaves this central carbon missing an octet. But again, here we have two choices for where an atom can share an extra set of electrons. We could go there, or we could go there, which means that we have two resonance forms, right? There's one here, the double bond there, right? And if we look, here's an oxygen with one bond. We should start to be getting a feel for that. That looks odd. If we do our formal charge analysis, right, that's where the formal negative charge ends up, right? Alternatively, we would have this structure, right? If we drew the results of the blue arrow, and so that gives us then, right, two structures, both of which are equally stable, so one is not favored over the other, and they are resonance structures of each other, which we represent by this single line two-headed arrow. That means these two structures are resonance structures of each other. We can use curved arrows to show the interconversion of these two structures, right? And so one of the things we can do is, we could show one of these pairs falling in and the pi electrons coming back out. That would show the conversion of this structure into that structure, right? Conversely, we could go backwards by showing this pair of electrons falling in as this pair of electrons moves out. That's the conversion of this structure into that structure. So we can use curved arrows to show the movement of electrons within a structure to show the interconversion of these two resonance structures. Okay, so now we'll look at a species C3H5 plus, which we'll call the allyl cation. Now, this is one of those cases where having an indication about the connectivity helps, right? And so I will let you know that the carbons are in a row. There's two hydrogens on that end, a hydrogen in the middle, and two hydrogens on that end. And in this case, we have a single pair of electrons left. And since we only have one pair, I'm going to put them in the middle, right? So after we've drawn our structure, counted up our valence electrons, distributed them, we end up with one pair left. So we have a choice now, right? Because we have, right, this carbon doesn't have an octet, but this carbon doesn't have an octet either. And so we're in a situation where we have to choose. And so we could go left and create this kind of ion with a double bond here. But a formal charge analysis would show us that the positive charge then, the formal positive charge lies on that carbon. We also could consider the electrons go this way, giving us a structure like this. Giving the right carbon the octet, but leaving the left carbon electron deficient, and then the formal charge lies there. And again, we have a situation where we have two resonance structures. Now, one of the things we can do is we can show the interconversion of these two resonance structures, again, by showing electron movement. So to go from left to right, the electrons in the pi bond could shift over there. So we can use a curved arrow to show the interconversion. And conversely, to go right to left, right, we can show the pi electrons moving over there. So we can use arrows to show the movement of pi electrons to show the interconversion of resonance forms. Now we'll consider the CH2COH minus, or the acetaldehyde enolate ion. Okay? Now again, connectivity is important here, right? Note we've got this thing we've seen before, carbon or oxygen right after a carbon in the formula, which means that oxygen is attached to that carbon. Whatever's after the oxygen is attached to the carbon. And so that gives us a connectivity that looks like this. Right? And when we distribute our electrons, we end up with this when we run out of electrons to distribute, which leaves us with this central carbon without an octet, but it's adjacent to atoms with unshared pairs. And so, right, that pair could fall in, give us a structure that looks like this. Right? Formal charge analysis will show us that the negative charge is on that oxygen. Right? Alternatively, one of these pairs of electrons can come in to give that central carbon an octet, giving us a structure like this. Right? That still has its unshared pair now. This is where the double bond is. Right, with a hydrogen, and formal charge analysis puts the negative charge there. Right? So again, right, we have created two resonance structures, but in this case we've created two non-equivalent resonance structures. Right? Here the negative charge is on an oxygen. Here the negative charge is on a carbon. Now, in each resonance structure, everything has an octet, but since they both have an octet, the negative charge being on the more electronegative atom makes this left structure the preferred structure, what we consider the more stable resonance form. And again, right, we can show interconversion, right? And so to convert the left structure to the right structure, pair of electrons from that oxygen would come in, freeing the pair of electrons, the pi electrons to move to the carbon, and so that would convert this structure into that structure. Right? In the same way, we can use our curved arrows Those electrons can fall in. These pi electrons can move away to, keep that carbon at an octet. And so those arrows would show the conversion of this structure into that structure. Let's consider the C3H5 neutral species, what we'll call the allyl radical. Right? And so in this one, let's quickly go through our electron sum, right? So if we look at this, right, we have 3 carbons. That's going to be 3 times 4. We have 5 hydrogens. That's going to be 5 times 1. So that's 12 electrons. That's 5 electrons. Gives us 17. Right? So when we draw our connected structure, it's going to be similar to one we've seen before. Right? It looks symmetrical, but we've accounted for here 1, 2, 3, 4, 5, 6, 7 bonds, which means we've accounted for 14 of those 17 valence electrons with bonds, leaving us with only 3 to distribute. Okay, so if we put 2 on the left side and only 1 on the right, we're out. Right? And so that leaves us with a structure with an odd number of electrons. Okay, so note here, right, here we have an electron with nothing to pair with it. That is the definition of a radical, right? A radical species is a species that has an unpaired electron in the final structure. Because we have an odd number of valence electrons, in the end, we're going to have an electron without a pair. That makes this a free radical. Okay? Now, we have this central carbon without an octet. And so, one of the things we could do to give it an octet is let this pair fall in, and that would create a species like this. Right? And there is our unpaired electron with a free radical. Now, everything that we've done so far has had an alternate resonance structure. This one is no different. Right? So if we take this, right, and use a different form of arrow, right? If one of these electrons moves over here, and note I'm denoting one electron by using half an arrowhead here. So one pi electron moves over, while the other one stays here. And then this one moves in to pair with that. Then we get an alternate resonance structure. Where now the double bond is here. And that has an unpaired electron. So those two structures are resonance structures of each other. And if we go through and do a formal charge analysis, we will see that this carbon, even though it looks odd with that unpaired electron, this carbon has no formal charge. Same thing here. This carbon has an unpaired electron. But overall, if we do our formal charge analysis, this carbon has no formal charge. So when we have free radical species next to carbon-carbon double bonds, we can get resonance. And if we want to consider the resonance in reverse, right, again, right, we use an arrow with half an arrowhead. That electron can move in and can pair with that one. And then the extra electron can move back there, and that would convert this structure into that structure. So here we have, again, two equivalent resonance structures, in this case for a free radical species. So that gives us some situations that we might deal with when we're dealing with charged or radical species in organic chemistry.